Hey CW Apes, Mr. Kennedy here. Today I have a very short video on risk analysis for you that goes along with all the information we're learning in Chapter 10 on risk for environmental science. First question I have for you is who performs risk analysis? Well, when we think about risk, I'm not just talking about the board game. I'm talking about like dangerous things that can impact human beings. Who's the person who's responsible, or what agency is responsible for evaluating risk in anything we might come in contact with in the outside world? One really important agency that takes up that task is the EPA, the Environmental Protection Agency. Now, they're not alone in their work, but this is one that I want to focus on for environmental science. The Environmental Protection Agency began in the 1970s, and basically its role then was really just to estimate cancer risk as a result of exposure to any type of chemical that we as humans or society might come in contact with. So when we think about risk and we're trying to figure out, like, is something dangerous, we're going to start with what's called a risk assessment. Risk assessment begins by determining the types of hazards that people are going to be exposed to, the probability that each of those hazards will occur, how many people might be exposed, and how many will suffer serious harm from whatever it is. There are two types of risk assessment or strategies that are employed when we're trying to figure out what's dangerous and how dangerous it is. The first one is called epidemiology. Epidemiology tracks how sickness can spread through a community and establish links that way. Unfortunately, the other type of risk assessment involves animal testing. Animal testing, it has its proponents and people that are staunchly against it. It is one way of evaluating risk. It gives some immediate results, right? And one good case in point were the cats that they used in evaluating mercury levels in Minamata, Japan. I don't know if you remember that from a past video or not, but that was something that came up, okay? Next thing after risk assessment is a dose response assessment. A dose response relationship has to be determined between whatever we're exposed to and us, and how much of it do we need to be exposed to before we're going to get sick, and how sick are we going to get when we get exposed to whatever level we're exposed to. So the dose response relationship really is about how much of a substance do we need to get exposed to before we actually get sick, and what level of sickness will we get from that exposure. Your dose is the amount of a substance someone's taken in. You could have acute or chronic exposure to whatever that is. An acute exposure is a single dose, maybe exposure over like a very short time period. Chronic exposure is the exact opposite. It could be a longer period of exposure or multiple doses. In the dose response, we also have to look at the type and amount of damage that's going to occur. So we're going to revisit those two terms, acute and chronic, from the previous slide, but here we're going to use them to describe damage and not just exposure. The acute effect is an immediate or rapid reaction to exposure. And the chronic effect is the permanent or long-lasting effect. So if you think about it this way, exposure to cigarette smoke might cause the acute effect of an asthma attack or coughing, wheezing, runny nose, something like that, whereas the long-term exposure to cigarette smoke might be lung cancer, emphysema, or COPD. Right? So that's the dose response assessment in terms of damage that is done. Now, we can actually like graph these things, and this is an example of how we would do so. There are linear and also threshold relationships that can be mapped out through graphs. In a linear dose response curve, there's immediate there's an immediate response, like from the example I gave you before with smoke inhalation, where you're going to start coughing and things like that. The more exposure you get, maybe the more coughing you do. So that creates a linear graph if you were to chart it that way. In the threshold dose response curve, well, in this case, there's like no response for a while until you've reached a threshold, at which point now all of a sudden, like, you get really sick really quick. So in threshold, there's no immediate response. Levels basically have to build up for a while before we actually see any issues as far as illness is concerned. An example there might be lead or mercury poisoning. If you're exposed to mercury, you might not see any negative ramifications of that until you've been exposed to it again and again and again over the course of days, weeks, months, or years. And then suddenly one day, your nervous system is a wreck, right? So that's the threshold response versus the linear response. Range of tolerance also has to be considered when we're talking about risk assessment. All species have minimum and maximum levels of tolerance to any environmental factor that they encounter, which is absolutely necessary for their survival. You really couldn't live outside really at any stretch of the imagination for any time period unless you had some range of tolerance. I mean, you got to tolerate heat, you got to tolerate cold, you got to tolerate wet, you got to tolerate dry, but you also got to tolerate like chemicals, toxins that you might be exposed to, right? There's a minimum and a maximum level that you have to be able to tolerate regardless of where you live or what you do. Okay, so in terms of minimum and maximums, right, at the minimum level, like, this is the minimum you can tolerate and still be okay, and at the maximum level, this is the absolute most that you can tolerate and still be okay. Range of tolerance was explained through a different video when I was looking at how it impacted population growth. You might remember this graph where we were talking about fish, and in this case, these fish maybe are responding to temperature in an aquatic environment. Now, we don't really think about temperature as being toxic because, we're humans, and if it gets hot, we sweat or you turn on the air conditioner or whatever. But to a fish, if you're in the water, like, sweating's not an option, okay? So there's maximum and minimum temperatures that the fish can tolerate. And if you go outside of that, remember what we learned in that previous video, you're going to get to a zone of physiological stress. And if we keep pushing the envelope, eventually a zone of intolerance where your population dies off. Another thing to keep in mind when we're looking at risk assessment and tolerance and how this might impact humans is solubility. Solubility is basically the quantity of a particular substance that can dissolve in a solvent. So, when we're talking about solute and solvents, we could be talking about something dissolving in water, or we could be talking about something dissolving out into the air in gaseous form. It really doesn't matter. The amount of solubility of a gas or a liquid, a chemical, a toxin can increase the impact that it has on life. So if something's highly soluble, a few drops can spread out rapidly, and their toxic effect can impact more and more people or individuals in the environment. One of the most important characteristics determining how a toxin will move through a body or the environment is solubility. Now, when you think solubility, again, air, water, okay? There's another one that I want to throw your way, and that is fats, oils. So water-soluble compounds obviously go through water. Air, those are gases. Fat-soluble compounds, they go through any kind of oil. Now, if we just focus on these two, water and fat-soluble compounds, water-soluble compounds are going to be things like vitamin B, vitamin C, and they move through all of the fluid or liquid components of your body. Fat-soluble compounds, well, they penetrate into your body cells, and then they stay inside the cells or in your fat tissues and can be very hard to get rid of. Most water-soluble compounds, if you drink a lot of water and then urinate, like they're flushed out of the body. Fat-soluble compounds, they stay with you. So we have to be very, very careful about exposure to those things because once they're in you, it's very, very hard to get rid of them. Next thing we got to look at is how we measure toxicity. Measuring toxicity is usually done through what we call an LD50 experiment. LD stands for lethal dose, and then the 50 is for 50% of your population. So LD50 is how much of a chemical, a material, a gas, however you want to look at it, does your population have to be exposed to in order to be fatal or to kill 50% of the population. Okay, so here we have a graph of an LD50 experiment, which illustrates, that whatever this dose is that was being given to whatever creature, right here on this curve, that's where we get the lethal dose for 50% of the population. Okay, now I'm just going to tell you, the smaller that number is, the lower the LD50, the more toxic we believe things to be. Because that basically means teeny tiny amounts of whatever this is super toxic and going to kill more and more things, right? If you have to take a mega dose before it's toxic, well, then we don't really think of it as being toxic, okay? Here's some examples, all right? So as I said, the smaller the LD50, the more toxic the material. Water, right? If you think about water, there is a such thing as too much of a good thing. Like 90,000 milligrams per kilogram of various species could be toxic if you were drinking that much water. Table salt, 3,000 milligrams per kilogram could be toxic. Ethanol, 10,000 milligrams per kilogram. Check this out. Botulism toxin, 0.00001 milligrams per kilogram. That is a very small number. Botulism toxin is very, very dangerous. And in the olden days, it used to make a lot of people sick from improper canning and food preservation. Now, exposure assessment. Third thing we got to look at here. Exposure assessment is basically just estimating the intensity, duration, and frequency of human exposure. What are we going to do to protect ourselves? And like, how much can I be around this before I get to those, levels of toxicity that are measurable in the realm of LD50, right? Is it going to be an acute exposure? Is it going to be a chronic exposure? Like, what do I have to do here, like, to protect myself? So exposure hazards basically involve more people that are exposed, the greater the risk. The closer the people to the source, the greater the risk, right? That's how we evaluate exposure assessment. So if there's tons of people very nearby, greater risk. If, we're looking at chemical plants and things like that, we don't want to put a fertilizer manufacturing plant that has lots of ammonia in it in the middle of a housing tract, because you're going to have all kinds of people in close proximity to a chemical that is potentially very, very dangerous. Okay, all right, last thing, risk characterization. So once we put all this information together, right, in the first 3 steps, we'll be able to determine the magnitude of risk and its accompanying uncertainty. All right, ladies and gentlemen, that is how we evaluate risk for people. I hope you've learned a little bit about risk analysis. I'm Mr. Kennedy, and I will see you next time. Stay safe, everybody.